on. All right, so good afternoon, everyone. Thanks for coming to the second lecture of our course on numerical analysis of electrical devices. And today we're gonna talk about magnetostatics and start discussing the concept of inductance. And we will continue the other lecture with the focus on transformers, eddy currents, and some other quasi-static effects. Okay, so today we're focusing more on magnetostatics. Yeah, so let us recall very quick what we discussed last time, right? Last time we discussed we introduced the Maxwell equations, and we said that we will be discussing them in different arrangements. The first arrangement was the electrostatic, when the charges are static and no change in electric and magnetic fields. Right, so, and today we will be discussing the magnetostatic, basically the electromagnetism of static currents and the field without any change in time. Right, so these are the four Maxwell equations. We discussed them last time. Just really quick, the first one, again, describes the divergence of electric field, which is defined by the electric charge in a system. The second one, which is the Gauss law for magnetism, implies that there are no magnetic charges in nature. The third one is the Faraday law of induction, which indicates that any change of magnetic field in any point of a system unavoidably create the curl of electric field in the same point. And the last, Ampere's law, right, which indicates basically the opposite, that the change of electric field creates the curl of magnetic field. And also the current also creates this curl of magnetic field. Yeah, so these are the Maxwell equations. In electrostatic, we imply that the electric field doesn't change in time and magnetic field absent, right? And from these assumptions, we derive the main electrostatic equations, which is the Poisson equation for the electric scalar potential phi. We said that this is important because any solver essentially solves this Poisson's equation for the scalar field, because it is just one function to be solved, rather than in contrast to electric field, which gets three components, and you need to solve three equations for each component. For the scalar field, you can solve just one equation in any point of the system, and then using this definition of the electric field through the gradient of the scalar field, you can simply calculate the electric field in any point. In particular, this ANSYS solver, it solves this Poisson equation for a particular system. From these equations, we derived the Coulomb's law, right? We discussed how what kind of electrostatic field a single charge creates, and what is the force between charges and how they interact. And from this equation, we derived or discussed uh, the peculiarities of the electrostatic field in metals, conductors, and dielectrics, insulators, right? And our first lab was about calculation of the capacitance in a system of two uh, parallel plates, metallic plates, which is the system to store electric charge. Store electric charge. Yeah, so let us today start again from the Maxwell equations. Now we require the electric field to be absent, so no electric field. And again, all the fields, I mean, magnetic field is static, so no change in the magnetic field. How the Maxwell equations change in this case? Right, so starting from this equation, without the change of the vector d, of the displacement vector, we've got this equation that defines the curl of magnetic field in any point. Right, so basically it is equal to the current. Another equation for the curl of electric field without change in magnetic field is simply equal to 0. So the curl of electric field is 0. So from this we deduce that the electric field in magnetostatic must be the curl less. So no vertices of no vertices of electric field. Magnetic field, as usual, no divergence of magnetic field, which means, by the way, that any force line of the magnetic field must be the closed, like a closed line across closed loop. So no starting point, no ending point, always closed loop. This is fair for any type of system whatsoever, just any system. This is because no magnetic charge in nature. In the same time, the fact that the divergence of the magnetic field is 0 allows us to write magnetic field as a curl of some other field, because the divergence of curl is always equal to 0. So this is true for any system in general. Okay, so we introduce a new type of vector field, which is a capital vector field. This field is called vector potential field, and by definition, and as I said, in any case, it is fair for any system. Magnetic field is equal to the curl of scalar, the curl of electric vector potential, curl of vector A. And yeah, so one can ask why we need this new type of field, because in contrast to electrostatic, when we had a scalar field, which allows us to solve the equations, for example, numerically. It is a simplification because instead of solving equations for three components, you have just one function, scalar function. Uh, in this case, the answer is rather kind of fundamental. It is interesting from fundamental point of view. In fact, mm, in fact, this vector potential A has a lot of uh, consequences and properties that are useful for quantum theory. Okay, so and at the same time, this field, which is also called gauge field, so this gauge field uh, can be demonstrated that this field actually exists in nature. Okay, so this is tricky point about this vector vector potential field A, but yeah. So and yeah, as an example, I put this concept of uh, gauge freedom, um, which is basically the consequence of the definition of this field, right? So since magnetic field is defined as the curl of field A, then because due to the fact that curl of any gradient must be equal to zero, right? You can always write this potential field A as you can always add a gradient of any scalar field kappa, okay, to this vector potential field A, because curl of any gradient is equal to zero. So this change in the potential doesn't change the magnetic field. Okay. Yeah, I mean, we will probably touch upon this point of gauge freedom once again. Then we will talk about the electromagnetic waves. So light turns off. Few words about the magnetic properties of materials and how the magnetic properties, magnetic response arise. Right. So essentially, any magnetic response of any system is due to any type of loop of current. Okay, so here, like schematically, I put this picture of a loop with the current circulating around this loop. This loop of current creates magnetic fields, and these lines of magnetic field are shown in this red field lines. How we can describe this system and its the properties of this system? We introduce magnetic dipole, just like in the case of electric dipole, which is the system of two charges. Here, by, let's say, duality, we introduce the concept of magnetic dipole, which is equal to the to the current that circulates in this loop times the surface area covered by the surface of the surface of this loop, or the area of this loop. So you see, it depends on the geometry, basically the size. The larger loop gets the larger magnetic dipole, and also the current. The larger current, the larger this magnetic moment. In materials, these loops, there are no loops in the magnet, right? We all know about this magnet, and there are no metallic loops there, but still they get some circulations of electrons, like orbit movement of electrons that effectively create this loop of current, right? In this case, this current will be just the product of the charge of the electron times the velocity of this electron. Response of one single loop of current is negligible in this case, but if you sum up the response from many of them, you will get the noticeable effect, right? So here I try to illustrate like an array of current loops or magnetic dipoles are placed in the magnetic field H. Okay, so by definition or by an agreement, the magnetic field in free space is H field. Okay, but as this magnetic field is applied to a material with these loops of currents, the magnetic field, of course, is changed because the presence of this material. We describe this process of orientation of the dipoles, magnetic dipoles, along the magnetic field by magnetic susceptibility. Okay, so or magnetic polarizability, which is basically the same thing. So our material can be magnetically polarized, right? And this magnetic polarization changes the field through the induced magnetization. Okay, so this function m is, or quantity m is the magnetic, magnetization. So because of this magnetization, the field H is changed, and this is why we introduce a new field B capital magnetic induction, or magnetic field B. Just like in the electrostatic, we saw how the electric polarization of a material, of a dielectric, changes the vector E, and we need to introduce a new quantity, new field D, right? Electric displacement field to describe this new field. Here, similarly, we need to introduce a new field, field B. And the connection between the two, B and H, is through magnetic permeability, mu, magnetic permeability. The larger this permeability, the stronger the effect of presence of our material and its effect on the vector H. Okay.
Dr. Krasnok, I'm sorry to interrupt. So what you're saying is that this magnetic polarization, this M, it's like an equivalent to the electric polarization just now because of magnetic field.
Correct. Yes.
Okay. Okay. Thanks.
Yeah. So basically, just like in electrostatic with electric dipoles that can orient along electric field, here in magnetostatics, we have these magnetic dipoles that can orient along magnetic field. And this orientation of magnetic moments, magnetic dipoles, change the field within this material. Yeah, so this is essentially why we need to have this vector B, and magnetic permeability mu. The larger mu, the larger this effect on the magnetic field. Yeah, so thanks for your question. Don't hesitate to ask any questions during the talk, right? Just as usual, I like to have these like small discussions. Yeah, so depending on the effect of magnetic field on media, we can classify materials in 3 or 4 different categories or types, right? The first category is diamagnetic materials. So diamagnetic materials without applied magnetic field, they have no magnetic dipoles, okay? So basically they consist of atoms with paired electrons. I mentioned this loop of currents, right? This orbital movement of electrons, like in hydrogen atom, you have this nuclei and electron moving around this nuclei like this, and which is effectively the loop of the current loop. In fact, there is another cause for magnetic dipole, which is called spin, which can be understood as the self-rotation of electron or proton. Okay, self-rotation, and this self-rotation also creates magnetic dipole. And in materials with 2 electrons, for example, 2 electrons, where one electron rotates, for example, counterclockwise, and other electrons rotates clockwise, and they compensate each other. So, and in general, like overall, no magnetic response. So in these materials, without applied magnetic field, there are no magnetic magnetization, no magnetic dipoles, shown here by these empty circles. But when applied magnetic field, this magnetic field induces the magnetic dipoles. Okay, and this induction of magnetic dipoles are oriented in a way to compensate the magnetic field in the material, compensate the external magnetic field. So these magnetic dipoles, they are oriented in the opposite way to the applied magnetic field. We call these materials diamagnetic materials. This opposite orientation of the magnetic dipoles makes the magnetic polarizability negative, and mu permeability less than mu zero. Mu zero is the constant. Also, the fact that this material kind of resist to the existence of the applied magnetic field, it leads to the fact that this material kind of repulses the magnetic field from itself, right? From the material. So it repulses it, and this repulsion leads to some interesting effects. For example, here, this picture demonstrates the experiment with two magnetic poles, which create quite strong magnetic field between these poles. And between these poles, you see this cubic body made of bismuth. Okay, so this bismuth material, it is a natural diamagnetic, so it repels magnetic field. And using this repulsion, you can make this this body levitate between the poles of the magnet. This effect is quite small, quite weak, and does not doesn't have any in common with the superconductivity effect, which is the Meissner effect. Probably some of you saw this nice experiments with superconducting coils, or at least magnets levitating over the superconducting or bodies. This effect is much weaker and doesn't have anything in common with superconductivity. Another effect or another type of materials is a paramagnetic material. This material initially, like intrinsically, gets some magnetic dipoles. Okay, and in the presence of magnetic field, these magnetic dipoles orient along the magnetic field. Okay, so this mechanism of this magnetization is different, and because of this orientation of these magnetic dipoles along the magnetic field, the magnetic field inside such a material is increased. Okay, so it's this induced magnetization inside of this material kind of leads to the enhancement of the magnetic field in such materials. Again, the effect is quite weak, but can be detected, demonstrated in experiments. And here I took a picture of another experiment. Again, here on the left and right, you see the poles of a strong magnet with two metallic spheres, okay, that form a small gap. Okay, so this is the small gap between two spherical particles. And then here in the middle, this white thing is nothing but the liquid oxygen. Okay, so liquid oxygen or just oxygen is a typical substance with paramagnetic response, paramagnetic property. And the fact that the the atoms of oxygen orient, or magnetic dipoles of the oxygen orient along the magnetic field, makes oxygen to kind of attract, or it attracts magnetic field, right? So it can form such a bridge between two poles of a magnet. So, and this is what you see here. The bridge, kind of the small bridge of liquid oxygen between two poles of a magnet. So this is kind of a funny fact. If you have a magnet, right, in atmosphere, we of course have oxygen in atmosphere. So if you have a magnet, okay, there is a slightly larger concentration of oxygen around the poles of your magnet. Okay, it's kind of increased concentration of oxygen around the poles of your magnet. For example, in contrast to nitrogen, nitrogen is an example of diamagnetic. So nitrogen is kind of repulsed from your magnet. Oxygen instead is attracted to the magnet. And finally, the third type of material is called ferromagnetic. Ferromagnetic. Ferro means iron, right? This is why these materials got their names, because iron is kind of is the typical material with ferromagnetic response. So in contrast to paramagnetic materials, ferromagnetic, they not only have intrinsic magnetization, magnetic dipoles, but these magnetic dipoles already kind of strong and aligned. So they kind of grouped in microscopic elements called domains. And these domains provide a very strong magnetization effect. So in this case, this magnetic permeability can be much larger than mu0. The factor, the ratio between the two can be 100 or even 1,000. So this material strongly increase magnetic field in its volume. Another typical effect here is the effect of hysteresis, which is basically the fact that if you apply external magnetic field and then turn it off, the magnetization will be there. So okay, this is a material with a memory, right? This material remembers the magnetic field you used to create it. And some of you, of course, remember this audio, how is it, audio cassette, right? The audio films or magnetic films that people just recently used to record these audio files, music, and so on. Not only music, the video, VHS, right? VHS type of memory, and so on. So all this based on hysteresis. The first type of computer memory also use these ferromagnetic coils for the memory. Another effect is Curie temperature, right? Curie temperature means that if you heat your ferromagnetic material, it completely loses the ferromagnetism. It becomes a paramagnetic material. The fact that ferromagnetics interact so strongly with magnetic field can be useful and negative. And here I put a negative example of this interaction. So here on this picture, you see the coil of MRI scanner. This MRI scanner, it gets this coil that creates strong magnetic field in the center of this coil. And anything that is made of ferromagnetic material, like iron or nickel, like this office chair, will be attracted to the area with strong magnetic field. Okay, and also the stronger the gradient of this field, the stronger the force of this interaction. So people who work with these MRI scanners, they they put a lot of effort to kind of for the security, because any type of scissors or knife or I mean whatever, the key will be attracted to this magnetic field with very large speed, velocity that can hurt someone, a patient who is under the MRI scan. And there is a last one kind of material which is called anti-ferromagnetic or anti-ferromagnetism. It is essentially a material with the opposite orientation of these magnetic dipoles. Okay, so it's a kind of a specific state of a matter when instead of aligning dipoles, magnetic dipoles like this, all magnetic dipoles aligned in opposite way. They group like this and align in opposite way. So all these opposite magnetic dipole orientations lead to completely well, negative effect. So you got no magnetization because of this arrangement of the magnetic dipoles. So antiferromagnetics are materials with no magnetic response. And since they have no magnetic response, I didn't put them here. So a few words about magnets and magnetic fields. Of course, the kind of the easiest, the simplest source of magnetic field is this bar magnet, right? You can purchase one from Amazon, whatever. Yeah, it creates some magnetic field. The magnetic field lines start from North Pole, okay, and end in South Pole. And it looks like here we get two poles where the lines start in the north and end in south. But in fact, these lines continue inside the magnet. Okay, so all these lines are closed. Okay, so yeah, these lines continue inside the magnet. This is another example of a magnet for sure. Magnet, right? Again, the lines kind of start outside of the magnet in external exterior. The lines start at north and end in south, but again, these lines continue inside of the magnet. Just like in electrostatic, the same poles repulse, repel, the opposite poles attract. Another kind of example of a source of magnetic field is which is always around us is the Earth's magnetic field, right? Fun fact here is that, so this is North Pole, North geographic pole. This is South geographic pole. But if you notice that the North Pole, the magnetic lines actually come to this pole, right? It means that this is kind of south magnetic pole. So fun fact is that north geographic pole is south magnetic pole and vice versa. South geographic is north magnetic. What else? Yeah, a couple of kind of nice, interesting facts. The fact that our planet gets this noticeable and measurable magnetic field made the birds to navigate in this magnetic field. Okay, so birds, they get these magnetic sensors in their heads that allow them to kind of see or feel magnetic field. And they use these magnetic field lines of Earth's magnetic field for navigation. Okay, so birds are sensors of magnetic field. This is fun fact. At the same time, of course, today we've got a lot of electricity systems, machines, things that create strong magnetic field, and that's not healthy and good for birds. There are many types or many times when like strong the systems with strong magnetic field, like transformers, for example, okay, they cause some problems to to birds. So this is something to remember about. Another fact, pretty important one, that our Earth's magnetic field actually protects us from sun's radiation. Sun emits a lot of charged particles like protons, electrons, and these particles create different ions and so on, which are harmful to us, and the magnetic field protects us from this dangerous and harmful effect of radiation. Without magnetic field of Earth, life wouldn't be possible on our planet. Okay, so few words about what happens when we have some charge moving in the magnetic field, right? This is kind of experimental fact that if you have a charge and this charge is moving in the magnetic field, the effect is so-called Lorentz force. And the formula is here. So this force is defined by the charge of the value of the charge, velocity, and the magnetic field strength. So the larger the charge, the larger the force, the larger the speed of moving, the larger the force, and the larger the magnetic field, the larger the force. Another point to notice here is that if the charge is standing, so no movement, the force is zero. So magnetic field acts only on moving charges. Okay, so if charge doesn't move, no effect of magnetic field. Without these moving charges, it is impossible to detect magnetic field. And in fact, actually, if you continue this logic, you will recognize that magnetic field is just another form of electric field. Okay, so magnetic field is just relativistic effects of charge moving. Without moving means current. Without current, no effect of magnetic field. And fundamentally, magnetic field is just another form of electric field. Okay. And in general, electric field, magnetic field, there are no electric and magnetic fields, right? This is another story to tell. And fields, electric fields, magnetic fields, just the concept, mathematical concept that we use to describe something about our system that agrees with the experiment, but still this is just the mathematical abstraction. Okay, so we have magnetic field and moving charge. The last point to notice here is that the force is orthogonal to both velocity and magnetic field. Okay, so for example, if charge would move along magnetic field, there is no force. So the force, the velocity must be kind of orthogonal, or at least get some angle with the magnetic field, and only in this case you will notice any force. So let us consider a piece of wire, okay, this indicated in pink here, placed in the magnetic field, which is oriented into the screen. And this wire moves from left to right. The fact that wire moves means that every electron that is sitting inside of this wire moves along with the current movement, right? So this moving creates current in space, not along wire, but in this from left to right. So you see that the magnetic field inside points into the monitor, the current from left to right, which means that the system gets this force, the Lorentz force, that acts on every electron in the wire, and this force directed to the down, right, from top to down for the negative charge, for the electron. So electrons will kind of push down to inside of this wire. And this is the result. So more electrons kind of go to the down, leaving more positive charges in the upper area here. And so the result of this moving of the wire in the magnetic field is depletion of positive and negative charges in the wire. Okay, so moving this wire allows you to kind of split positive and negative charges, and this will continue. So this positive and negative charges, they will create the electric field, of course, right? from positive charge to negative charge, which is the opposite effect. And the stronger you move, the more charges you deplete, the split, the stronger this electric field in it. And at some point, this electric field will compensate the Lorentz force. So essentially what I'm talking about is that this moving creates some kind of force that splits the charges. We call this effect, this splitting of charges, electromotive force. So electromotive force is the effect that leads to splitting of positive and negative charges, and it's used for generators, right? It's not practical, it's not feasible to move a piece of wire magnetic field. It's much more feasible to create magnetic field between two poles and then make a loop of this wire, or many loops, and rotate them in the magnetic field. This is how any generator works. And as this loop rotates, it creates this electromotive force, which is essentially the splitting of positive and negative charges, which is the voltage, right? This is why we measure electromotive force in voltage. And the Faraday discovered this law, which now bears his name, the Faraday's law, that the electromotive force is proportional to the time change of the flux of the magnetic field through this coil. Okay, so the flux is just the product of magnetic field times the area and the scalar, the dot product, and which is the maximal when the area of the loop is oriented along the magnetic field, minimum, which is 0 when it's orthogonal to magnetic field, and the the faster this rate of change of the magnetic flux, the larger the electromotive force, this EMF. Yeah, so we use this effect to generate electricity, for example, right? Any electricity around us is generated this way. Up to the point that our generators are free phase generators, so it's not one coil, it gets 3 coils, and but yeah, essentially this is the same thing. Let us look at this picture once again. One can ask, okay, can I, for example, rotate the instead of rotating the coil, can I rotate the the magnetic poles? Of course, yeah, it's the relativity principle, right? So it doesn't matter which part of the system you rotate, it will lead to change of the magnetic flux, and as a result, it will change. It will create the electromotive force of the system. Then one can ask, okay, can I just remove the magnets and get just the loop, right? And instead of rotation this loop in the magnetic field, I'm applying the current, which changes in time. Naively, I expect that this change of the magnetic current in the loop will change the magnetic field within this loop. And the change of this magnetic field within the loop will create the electromotive force in this loop itself, right? So indeed, this is how it works. Having just one loop or a coil and applying AC bias, alternating current bias, with changes in time, leads to changing in time of the magnetic field in the coil. And this changing in time of the magnetic field leads to the creation of the electromotive force in this coil, in this solenoid or coil. And by the Lenz's law, this electromotive force induced creates the magnetic field, which is against, like oriented against the magnetic field that caused this electromotive force. Okay, so you apply the current, this changing in time, this changing in time current creates changing in time magnetic field. This magnetic field changing in time creates the electromotive force in this coil, which creates the current, which is the opposite to the original one, which creates the magnetic field that tries or tends to reduce the change of the magnetic field. This is how it works. So yeah, this is the effect of self-inductance. Okay, of course, different currents will cause different. No, it's better say the same current, but in coils of different composition, of different shape, of different number of turns, of different size, dimensions. The same current will cause different flux, different electromotive force. Okay, and we introduce the concept of inductance here and denote this inductance by L capital, which takes into account all these factors, the turns, the shape, the size, and so on. So it defines the self-response, self-inductance of the coil in response to the particular current. Okay. And plugging this formula for the magnetic flux to this Faraday's law, you come to this equation for that connects the electromotive force with the change in current in this coil through the inductance. Like one angle to look at this effect of inductance is to compare inductance with inertia. Okay, so when you, for example, you are in the car and trying to start moving, right? You feel this kind of force that pushes you back against the move. Or when you are in the car or in a bus and the bus suddenly stopped, you kind of some force, right, moving pushes you forward. So it is kind of inertia is a force that does its best to keep you in the same state, moving or rest. Just like inductance works the same way. And in fact, there are some theories that kind of connect inductance and inertia. So yeah, so inductance, if you have inductance, it will try to keep your system, your circuit, for example, in rest as much as possible, right? For example, if you consider even one single wire and ask how fast I can drive the current in this wire, like what would be the largest frequency? And the largest frequency can be somewhere in gigahertz, for example. And this will be defined by the inductance of the current. And for a single wire might be not very important, but if you create a processor, okay, so the electronic processor that our computers use to work with data. So these processors, of course, they got these connectors, and each connector gets its inductance. And there is a fundamental frequency above which you cannot use your processor because of the self-inductance of every single conductor. So that's why it's so important to know about this and be able to calculate inductance of any wire. any
Professor,
system, yes.
I have a question. So, this opposition, the opposes charges in the current flowing through it by generating EMF. We said that the EMF is when the positive and negative charges trying to split, right? Or
Yeah.
so that's how the opposition is created, basically.
So this opposition, not the opposition to this experiment. This is the reason or the cause for the electromotive force. What actually happens in the coil, you have some kind of generator that you use to drive current in this coil, some sort of generator. So let's call this bias, okay, the current bias. And let's say you drive it with a sinusoidal function. So your current first grows and directed directed what's it, counterclockwise in this picture. So this will create the electromotive force which with the opposite polarity to your generator. And this opposite polarity will push these electrons back, trying to kind of stop them. And this pushing them back in the opposite way essentially creates the current in the opposite way. And this current in the opposite way creates the magnetic field around this current, which is also opposite to the bias field. So this is how it works. Inductance wants the current stay unchanged. If the current is constant, no inductance effect. If the current changes, there is an inductance that tries to return to stop your current, stop your electrons, and cancel down the change of the magnetic field.
Thank you.
Yeah. Yeah, so we said that it's important to calculate inductance for many reasons, right? And one chrestomatic system, which is very well known from the theoretical point of view, is called solenoid. So a solenoid is a coil with many turns, and it's long enough to consider magnetic field inside the solenoid, inside this coil, as homogeneous. Okay, so we consider magnetic field inside solenoid kind of constant. Better say homogeneous. It can change in time, in direction, but the amplitude of magnetic field doesn't change in this lateral dimension in the cross section. In this case, we can use a theory. We can apply the Curl-Gauss law, the Maxwell equation in the integral form, to obtain the formula for the magnetic field inside the coil, inside the solenoid. This is the result. What is important here is that this magnetic field is proportional to the number of turns and the current in the solenoid. The larger the current, the larger the magnetic field, which makes sense. And also the number of turns. The more turns, the stronger magnetic field. and also proportional, by the way, to the magnetic permeability. So let's say if you use diamagnetic, this magnetic field will be reduced, but if you use ferromagnetic, this magnetic field, B field, can be increased by many times, hundreds, maybe thousands. For the given magnetic field, we can find the magnetic flux simply taking a product of the magnetic field by the cross-section area of the solenoid. This is the result. This is the total flux from all turns, right? Which goes through every turn, every single turn. And the total flux through all these turns will be multiplied by n, right? So I need to take this flux through single turn and take a product by the total number of turns to get the total flux. So you see that this factor of number of turns comes to this calculation kind of twice. And this is important fact. So the inductance, of course, is the total flux you divided by current. And this is the formula. And the formula you see depends on the number of turns to the power of 2. So the kind of more turns leads to greater inductance, but it's not proportional, but the power of 2, quadratic dependence. So it makes sense to, if you need to concentrate magnetic field, if your goal is to increase this inductance as much as possible, you need to make more turns, because twice larger number of turns, 4 times larger the inductance. In many applications, you need to reduce inductance. For example, this example with CMOS electronics and processors. In that area, people avoid any turns. Okay, so the less kind of deformation of wire, the better, because any deformation, any loop, any bend will unavoidably create the stronger inductance. Few words about applications. About n squared, I said, there is another factor of the permeability. The larger permeability, the larger inductance, and vice versa. And why it's important? Well, if you want to detect, for example, some metallic objects, right? Typically, metals get strong permeability, large permeability. And here on this picture, you see the security gate in an airport. Okay, so the security gate essentially is just a coil. Okay, just a coil driven by some current, from which you can deduce, you can figure out, calculate the inductance, but essentially it's just a coil. And suppose you have something in your pocket, like metallic, a knife, whatever. This presence of metallic thing will cause the change of the inductance, and you will detect that through the change in the current. Okay, so for the security purposes, it's very important fact. And it is quite important that this approach is very straightforward and very simple. So it's just a simple dump coil. Okay, so it's very cheap, and cheap means cheap and reliable. Cheap and reliable means good. Another example among hundreds and thousands of other examples is this metal detectors, right? You have this coil in here. This coil gets some inductance, and as this coil comes to any metallic thing, rings, coins, it will unavoidably change this inductance, and you will be able to detect that. The actual principle, of course, a little bit different. You use the AC currents there and so on, but the principle is something like this. Finally, a few words about mutual inductance. Okay, so what happens if you have two coils? So let's say again, you have coil 1 and you drive the time changing current in this coil 1, and which creates the changing magnetic field. And of course, this coil gets its self-inductance that tries to stop this change of magnetic field and stop the change of the current. but the magnetic field around this coil 1 changes, and this changing of magnetic field of the coil 1 creates the change of the magnetic flux in the second coil, right? This change of magnetic field in the second coil, due to the Faraday's law, creates the electromotive force in the second coil. So the first coil induces the current or voltage in the second coil, right? Even though there is no like wire connection between them, all this happens wirelessly. And just like in the case of self-inductance, the mutual inductance can be introduced similarly, but now this mutual inductance defines it is the coefficient, the proportionality coefficient between the change of the current in the first coil and the electromotive force in the second coil, and vice versa. You can write the same equation for the opposite connection, and you will see immediately that this the mutual inductance is the symmetric thing. So it's doesn't depend how you arrange them. I mean, it doesn't depend which one is coil 1, coil 2. This is symmetric thing. Application of this, again, many of applications. One systematic application is the transformer that we use to transform current to voltage, voltage to current. You know that just like magnetic field and electric field, just mathematical abstraction. And what is important is the form of energy. Okay, so this electromagnetic field is just new, or I mean, another type of substance, and it's described by energy. And the way how we describe it using electric field, magnetic field, or using photons, like in quantum physics, it's just the matter of how we describe it. Similarly here, currents, voltage, again, abstraction, but very nice and useful abstraction that leads to right conclusions and useful consequences. But the main thing is the energy, and transformer transmit energy from one coil to second coil, of course with some efficiency less than 100%, but while it transmits from one coil to another coil, you can increase voltage and decrease current, or increase current, decrease voltage, as long as the energy is conserved. We will talk more about transformers next time. And for the lab 2, right, you will be asked to calculate a solenoid, numerically define the inductance of solenoid depending on the number of coils, turns, and compare these results with the analytical formula which is presented here. So this is the end of my talk for today. Let me stop my recording and then we can discuss quickly.